So permutations and combinations is the new chapter for the session. To come with the introduction, what is permutation and a combination is the biggest question which starts with the introduction of the topic. When we talk of permutations and combinations, let me come with a real life puzzle or an example to start with how the permutations and combination topic has come into existence in the branch of mathematics. Say for example, I have say 3 sets of trousers and shirts available. Say this is 1 and this is 2 and this is 3. Now, so these are the 3 sets of trousers as we see here. Now, I want to see how the permutations and combinations are understood with this example. Say for example, this is trouser 1, trouser 2 and trouser 3, and this is shirt 1, shirt 2 and shirt 3 are the 3 basic set of trousers and shirts available, through which I want to see that now when I go for a party, I want to have a combination of this trouser with this shirt, or this trouser with this shirt, or this trouser with this shirt, or I want to know if I can wear this trouser with this, or this third trouser with the 3 of the shirts. So my trouser 1 has 3 possibilities. One is wearing shirt 1 with this trouser 1, or wearing shirt 2 with this trouser 1, or wearing shirt 3 with this trouser 1. Similarly, when I just change my trouser 1 into trouser 2 and see which is the best combination, then there are 3 possibilities of wearing 3 different shirts for the trouser 2. That is shirt 1, shirt 2 and shirt 3. And the same applies for the third trouser, that is T3, for which there are 3 possibilities: shirt 1, shirt 2, shirt 3. So these are the 3 different possibilities I see in wearing my trouser with the shirt, because I want to know my exact match of the trouser with the shirt. So I try with various attempts of wearing trouser 1 with shirt 1, 2, 3, and trouser 2 with S1, S2, S3, and T3 with S1, S2, S3. So with this I understand that there are totally how many possible ways of wearing a trouser and a shirt, the different combination of a trouser and a shirt. Then totally I see for this exclusive example problem as a puzzle that T1 S1 is one possibility, then T2 S2 is another possibility, and T3 S3 is the third possibility of the combination of a trouser and a shirt. Then T2 S1 is another possibility, and T2 S2 is fifth possibility, and T2 S3 is the 6th possibility, and my 7th possibility is wearing trouser 3 with shirt 1, then T3 with S2 and T3 with S3, with which I understand that there are 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are totally 9 possible ways. Therefore, it is possible that I can wear in 9 different ways of the combination of a trouser and a shirt. Of the combination of a trouser and a shirt. So this example problem of 3 trousers and 3 shirts comes with the biggest question put forth to every one of us on what happens if I have 100 trousers and 100 shirts, or how many possible ways I can just change my trousers and shirts if the number of trousers or number of shirts are increased, or what happens if I don't have exact number of trousers and shirts. Say I have 200 trousers and 100 shirts. So how many possible ways I can change my shirt with a trouser in place of this is the biggest question. So for such problems, it's quite easy to approach directly and find the number of possible ways of, in 9 different ways, the number of possible ways of combining a trouser and a shirt. But if the number of trousers or shirts, or the number of ways of which you can arrange increases, then the biggest question comes on how we understand the concept of permutations and combinations. So let's see in brief on what exactly is a permutation and a combination through the live examples, to be continued with the session. So the definition of permutation and combination is very important to understand the arrangement, or the puzzle, as we have seen in the previous example, is very much related to the permutations and combinations. So let's see the definition of permutation and combination in brief. Say I have 2 types of arrangements. One is permutations, one is combinations, which I'm going to take first, and next is permutations, which I take as the second definition. In this case, it is nothing but combination is the process of selection and here permutation is the process of selection and arrangement. So this involves only selection, but this permutation involves selection and arrangement. So this is a 1-step process and this is a 2-step process. This involves 1-step process, but the permutation involves a 2-step process. Is how we understand the difference between the permutations and combination. Now initially, to start with, the process of selection and arrangement, let's see what exactly does the 2 terms selection and arrangement mean through an example. Now, for example, say I have the digits 1, 2, 3, 4 and 5. So there are 5 digits 1 to 5 and I want to form a 3-digit number out of these digits. I want to select the digits 2, 4 and 5. Now when I select the digits 2, 4 and 5, the set of all the digits which are selected form a combination. Say for example, now in this case of the numbers 1, 2, 3, 4 and 5, the digits which are selected are 2, 4 and 5. Therefore, these 3 under the set form forms a combination. That implies, therefore, set 2, 4, 5 forms a combination is how I understand the combination, because it involves only one step of only selecting the digits 2, 4 and 5 written in the set form, and this is nothing but, it doesn't affect the order because this is nothing but same as 4, 5, 2 or 2, 5, 4 etc. is how we understand the set taken in different orders but is again the same. So finally, combination is the process of selection where the set of all the digits taken which are selected from the digits 1 to 5 are taken in the set form, which forms a combination. Now let's see the same problem how we can understand through the permutation. Say for example, my question is that again I have the same numbers 1, 2, 3, 4 and 5. Then my question here is how to form the 3-digit numbers using 2, 4 and 5. So I wanted to find the 3-digit numbers which can be formed using the digits 2, 4 and 5. Now here the process is not selection because already the digits which are selected are 2, 4 and 5, but here the process step 1 is selecting the digits 2, 4 and 5, and the step 2, which involves this 2-step process, is arranging them in to form a 3-digit number as the question desires. Forming the 3-digit numbers using 2, 4 and 5. Step 1 is about selecting the digits 2, 4 and 5, and next comes arrangement, because permutation is about selection and arrangement. One is the selection and then we're going to arrange to form the 3-digit number as the question desires in this case. So the possible 2-digit numbers which I can form as 2, 4, 5, 2, 5, 4, 5, 4, 2, 5, 2, 4, and then the other possibility is 2 or 4, starting with 4, 5, 2 and 4, 2, 5. So totally I have 6 different possible ways of arranging the digits, which is this, 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 this or this. Now in this case, this forms a permutation because the possible 3-digit numbers forms a permutation arrangement. This form a permutation. Now in this case, we understand that step 1 is about selecting and step 2 is about arranging the 3-digit numbers in different ways. All 6 possible ways through which I can arrange the 3 digits or the 3 letters or the 3 single digits into a 3-digit number using the different possible arrangements. And this forms a permutation and this forms a combination, is how we understand the difference between a permutation and a combination in real life example. Now that we have discussed about the difference between the permutation and a combination, it is very important that for a given problem we identify the selection or arrangement by understanding the situation of the problem. It is not directly given as a question related to a permutation or a combination, but a student themselves need to identify whether the given problem is based on the selection or the selection and arrangement. If it is a problem based on selection, we use the combination for that given problem. If the problem is based on situation of selecting and also arranging, as in case of this example problem, then we try to use permutation, is how we justify through the practice problems. Factorial. The factorial concept is very important because most of the problems related to permutations and combinations are related to factorial. So let's see what is factorial. The essentiality of permutations and combinations. Now we define factorial generally denoted for a positive integer n. Factorial is defined for a positive integer n where we denote the factorial of n by n factorial. This is read as n factorial. So this is read as n factorial and denoted with n exclamation mark out here. And n factorial is defined as 1 factorial if n is equal to 1, and this is n times n minus 1 factorial if n is greater than 1. That's how we understand n factorial. So the two ways of understanding n factorial, one is this is 1 factorial if n is equal to 1, and this is n times of this if n is greater than 1. So let's see how we can understand this more clearly through the example problems. Suppose I wanted to define n 3 factorial, then in this case I understand that n is equal to 3, which is greater than 1. Therefore, to find 3 factorial, I use this with this because n is greater than 1, n being equal to 3. So using this formula, n factorial is n times n minus 1 factorial. So 3 factorial will be 3 times 3 minus 1 factorial, which comes out to be 3 times 2 factorial is how we get. But again, since n is 2 here, which is greater than 1, I again use the second case of the formula n factorial for n greater than 1, n equal to 2 greater than 1 implies this will be 3 times 2 times of 2 minus 1 factorial. This is using this definition is how we get it. Then further simplifying this, 3 times of 2 times 2 minus 1, which is 1 factorial, is finally where this is equal to 1, n is equal to 1 implies, I use the first case where n equal to 1 implies n factorial is 1 factorial, which is 1. That is, I get this to be 1. 1 factorial is identified, that is, my 1 factorial is read as 1 factorial equal to 1 using this case. So 1 factorial equal to 1 implies this will be equal to 3 times 2 times this being equal to 1 is how we understand. Therefore, I get this to be 3 times of 2, which is 6. So finally, my 3 factorial is with the value 6 using the basic definition of n factorial. So this is how we find the factorial of a value by constructing through the different process. Now, there's an important thing to note that every time I use the factorial, I see that the numbers consecutively decrease by 1 unit until they reach 1. Therefore, my n factorial is defined as n times n minus 1, n minus 2, n minus 3, 3, 2, and finally 1 is how I understand the n factorial using the concept. That is, when I find 5 factorial, I can directly reduce this as 5, 4, 3, 2, and 1 until I reach the factorial up to 1. So when I find the factorial, I decrease the consecutive numbers in the product until I reach 1, decreasing by 1 unit each time. And hence, 5 factorial is 5 times 4 times 3 times 2 times 1. And n factorial is n times n minus 1, n minus 2 times 3, 2, 1 is how I understand the n factorial using the basic definition of case 1, n equal to 1, case 2, n greater than 1. Now, it is very important in understanding 0 factorial because there are many debates going on in mathematics researchers that 0 factorial is 1, and some of them say 0 factorial is not equal to 1. But finally, by convention, we conclude that 0 factorial is assumed to be 1 until and unless it is disproved that this is equal to 1. We assume by convention 0 factorial is equal to 1. There's no proof attached. So fundamental principle of counting is very important because it's a rule of counting process through which the permutation and combination problems are approached. So it is very important for the student to know the fundamental or the basic principle of counting before the permutation or combinations are introduced in the form of counting through arranging and selection. So let's see what does the fundamental principle of counting says out here. To revisit the example problem of the trousers and shirts, let me say that this is a trouser and this is a shirt, or let me say there's one more trouser and one more shirt, and next so on and so forth. Let me say there are M shirts So in this way, I want to take totally there are M shirts and N trousers is how I take the entire concept. So if I assume that there are M shirts and N trousers on the whole, then the question here is, in how many ways can I wear the shirts and trousers in pairs is the biggest question out here. So let's see how the fundamental principle of counting is used in case of this example problem. Suppose this is S1, S2, S3 or shirt M, and this is S2 and SM, and this is trouser 1, trouser 2, so on and so forth till trouser N, because there are N trousers. Then I see that in the previous case of 3 shirts and 3 trousers, here my shirt 1 I can connect with N trousers. So each of the shirt 1 can be worn with N different trousers. So there are N ways through which I can do that, because each shirt with N trousers can be worn in N ways is how I do this. Similarly, my second shirt S2, if I want to wear with each of the trousers, I can do that also in N different ways, because I can wear this with this with this totally in N ways, because there are N trousers through which I can wear one shirt and N trousers. This is possible in N ways. Now similarly, my shirt 3, if I wear with each of the trousers totally being N trousers, can be done in N ways. So similarly, if I proceed, then I see that my last shirt, which is SM, also can be worn with t-shirts T1, with trousers T1, T2, so on and so forth till TN in N ways. Now when I add all these, I get that each of the shirt which can be worn with N different trousers in N ways, N ways, N ways, has totally M shirts which can be worn in, therefore total number of ways, each of them being distinct, therefore total number of ways of wearing shirts and trousers in pairs is N plus N, each of N added, so that till M times, because the totally M of the shirts which are combined with N trousers in N ways in M possible times. So this N plus N till M times gives me N into M, that is Mn different ways, is how I understand. That is, my fundamental principle of counting makes me understand that if the problem is not about shirts and trousers but any other arrangements where I want to take M shirts or N trousers and arrange them in different ways. I can do that in mn different ways. The problem can be work 1 or work 2, which can be combined. If work 1 is done through m ways and work 2 is done in n ways, the total work is done in mn different ways, is how we understand the fundamental principle of counting. Now let's see the types of permutations. Now that we have discussed the permutation as a selection and an arrangement, a two-step process where we select the elements and we arrange them, is how we understand the permutation, as we have already discussed in the previous session through few example problems. Now, as we come with permutations, there are two types of permutations identified in mathematics. Now, when we discuss about the types, there are two types. One is the linear permutation, or this is also called sometimes as simply the permutation, is one type of permutation we identify, and the next is the circular permutation. So as the word itself defines linear and circular, we get an understanding that if the selection and arrangement is along a line, we call that as linear permutation, and if the selection and arrangement is along a circle, we call that as a circular permutation. So in this case, we define a linear permutation as selection and arrangement along a line or in a line is called linear permutation. We arrange them in a line. And here, selection and arrangement along a circle is called circular arrangement. A circle is called a circular arrangement. Now, what is the difference between a linear permutation and a circular permutation is the biggest question out here. How does it differ when you arrange and select along a line, or when you select and arrange along a circle, is what we need to understand when we talk of the two types of permutations, the linear and the circular permutation. So in this case, the permutation has its starting and ending element differ, but when you talk of circular arrangement, the starting and the ending element doesn't take into account, because we assume that for a circle there is no starting and ending point. It is a continuous circle which circulates back as a cycle, so doesn't include the starting and ending element along the circle. We have a cycle which is continuous, but we don't know which is the starting and ending element. Now, this concept is understood more clearly when we take an example problem and understand that more clearly. Now, let's see this example problem where I need to write all possible linear permutations and circular permutations using the digits 1, 2, 3, 4 taken 3 at a time. So I'm selecting 3 of the digits at a time, and I'm going to arrange them by forming 3 digits. Out of 1, 2, 3, 4, I select 3 of the digits and form a 3-digit number, is how I understand this problem. Now, there are two types of permutations which I need to represent. One is the linear and the circular permutation. Now, the question of circular permutation comes into existence because sometimes the questions demand for arranging the beads in a necklace. Now, as we know that a necklace is somewhat circular in shape, if you just take it, the number of beads you're going to arrange. So as the number of beads in a necklace form a circular shape, then selecting and arranging the beads in a necklace would be a circular permutation, but not a linear permutation, because the beads can never be arranged in the linear form in case of a closed round shaped necklace. So therefore, these kind of problems, as an example problem of the beads of a necklace, demands for a circular permutation but not for a linear permutation. So therefore, we try to just imagine through the situational problem of beads arranged in a necklace through a circular permutation, or if we take the number of racks put on a railway track for a linear permutation, is how we understand through the various examples of real life. So therefore, it is very important to equally know about linear and circular permutations together to do the problems based on their situational existence. So let's come with understanding the linear and circular permutations for this problem, where I'm going to form 3-digit numbers with the numbers 1, 2, 3, 4 taken 3 at a time. So initially, let me start with the linear permutation. So in this case, to form a linear permutation, I just have so many possibilities of taking 3 at a time. So initially, for the numbers 1, 2, 3 and 4, I have the different possibilities are 1, 2, 3 is 1 digit, then 1, 3, 4 is the other possibility, and 2, 3, 4 are the different possibilities of the numbers. So there are 3 different possible numbers I can form using the 4 digits 1, 2, 3 and 4. Now among themselves I can form various other ways of writing the 3-digit numbers. Now I have taken the digits 1, 2 and 3. Here I have taken the digits 1, 3 and 4. Here I have taken the digits 2, 3 and 4. Now when taken in different forms of 3-digit numbers, now the question comes in how many ways I can arrange this. If I take for example 1, 2, 3, next I can write as 2, 3, 1 and then 3, 1, 2 are the various numbers which can be formed with the numbers 1, 2 and 3. So in this case, the digits considered are 1, 2 and 3, for which I get this. Here I consider 1, 3, 4, through which I get this, and here I have considered 2, 3 and 4, through which I got this. Now once I have arranged this, then this is 1, 2, 3, 2, 3, 1 and 3, 1, 2. There are many other numbers which can be found with this 3 numbers 1, 2 and 3 as 3-digit number. Say for example 1, 3, 2, which is not existing, is also possible to construct a 3-digit number from the numbers 1, 2 and 3 by interchanging this. Then I get 2, 3, 1 can be done with 1, 3, which is arranged here. Then 3, 1, 2 is 3, 2, 1, which are obtained by interchanging each of the third and the second places of the digits. Similarly, 1, 3, 4, then when I go with the next 3, 4, 1 and 4, 1, 3 are the 3 possible digits which can be formed from the numbers 1, 3 and 4, and then interchanging the last 2 digits I get 1, 3 and 4 which are fixed, but the last 2 digits 3, 4 becomes 4, 3 and 4, 1 becomes 1, 4 and 1, 3 becomes 3, 1. Similarly, let me construct the various possible 3-digit numbers which can be formed with the numbers 2, 3 and 4. Now as I have here 2, 3, 4, the next is 3, 4, 2 which comes here, and then 4, 2, 3 which comes here. Now that the first 3 are fixed, I get 2, 3 and 4 which are fixed, and then the other 2 digits which are replaced. 34 becomes 43, 42 becomes 24, 43 becomes 34. Sorry, 23 becomes 32. Is how we understand the various possibilities which can happen with this. So these are the possible permutations of forming a 3-digit numbers taken 3 at a time out of the 4 elements 1, 2, 3 and 4. So here totally there are 6, and there are 6, and there are 6 which are possible when you add up. So therefore, as you see, there are 3 different ways of forming, but I think I missed out on 1, 2, 3 1, 3, 4, 2, 3, 4, but 1, 2, 4 is also possible out here, which is missing here. That is, when I take the element numbers 1, 2 and 4, I can also form a 3-digit number 1, 2, 4 using this. So proceeding with the same process, I have this 1, 2, 4, then comes 2, 4, 1, and then 4, 1, 2. And then finally fixing the first digits 1, 2, 4, and then I get 2, 4 reduces to 4, 2, 4, 1 to 1, 4, 1, 2 to 2, 1, which comes out with 6 different ways of forming a 3-digit number from the 4 digits taken 3 at a time. Now as I see here, totally there are the total number of permutations which is possible is by adding each of them. Therefore, the total number of permutations formed is, therefore, total number of 3-digit numbers which can be formed from the elements taken 3 at a time will be 6 plus 6 plus 6 plus 6, which on adding gives me 6 4s 24. Therefore, there are 24 different possible 3-digit numbers which I can form from the elements 1, 2, 3 and 4 taken 3 at a time. Now because you are taking this in the linear form of arrangement through the selection, we call this as a linear permutation. Now let's construct the circular permutation for the same problem by understanding the difference between a linear and a circular permutation. Now here comes understanding of circular permutation through the linear permutation. So with the linear permutations as formed here, which are 24 different possible linear permutations which can be formed, now let's see how this can be reduced to the circular permutation. Now the circular permutation has its order in a cyclic form. Therefore, it is understood that all these 3 are nothing but one single circular permutation. Because if I write this, say for example, the first permutation 1, 2, 3 in a circular form, I get this to be 1, 2 and 3 is understood as 1, 2, 3, 2, 3, 1, 3, 1, 2, 1, 2, 3, 2, 3, 1 and 3, 1, 2. So this is said to be in cyclic order, which forms one single circular permutation, is how I understand this. Similarly, if I take this, then I understand that if I just take this, say for the first permutation 1, 3, 2, say I take 1, 3 and 2, then I understand this as 1, 3, 2, 3, 2, 1, 2, 1, 3, 1, 3, 2, 3, 2, 1, 2, 1, 3 is how these 3 are said to be one single permutation this. So these 3 form one single circular permutation. Similarly, this forms one single circular, one single, one single, one single, one single and one single. So totally 1, 2, 3, 4, 5, 6, 7, 8. 8 circular permutations. So let's see what are those 8 different possible circular permutations. 1, 3 and 4. 1, 4 and 3. Then 2, 3 and 4 and 2, 4 and 3. Then next comes 1, 2, 4 and 1, 4, 2 is how I understand 1, 2, 3, 4, 5, 6, 7, 8. 24 linear permutations and 8 circular permutations. So therefore, I have 8 circular permutations. That is 8 different ways of arranging and selecting in the circular form, and 24 ways of selecting and arranging in a linear form. Is how I understand the 3-digit number, which can be formed by taking the 4 elements 1, 2, 3 and 4, taken 3 at a time. Now let's see the general formula of permutation. Now that we have discussed various examples of identifying the number of ways of selecting and arranging the objects or the elements, now here comes a general formula which can be applied for any case of selection and arranging of objects. So let's see how we can understand the general formula of a permutation. If n and r belong to z plus such that n is less than or such that r is less than or equal to n, then the formula says that then number of permutations of n dissimilar things, that is, they are not similar but they are all distinct to each other, of n dissimilar things taken r at a time, is given by the formula n times n minus 1, n minus 2, so on and so forth, till n minus r minus 2 times n minus r minus 1 is how we understand the formula. That is, this is taken in the form product of k running from 0 to r minus 1 of n minus k is how we understand the formula. So this is how we have this. So selection is r and number of things existing are n. So here it is important to note that r is the things which are chosen or selected, and then n is the total number of things which are taken into consideration. So total number of things taken into consideration is how we understand the n are associated with this formula. Is how we understand the permutation of n dissimilar things taken r at a time. That is, if I select r objects out of the n objects, then the number of ways through which I can select r objects from the total number of n objects is possible in this ways, is the direct formula which we have for permutation taken r at a time. Now the formula which we have derived for permutations, number of permutations of n dissimilar things taken r at a time is, we know that, is already taken by the formula n times n minus 1, n minus 2, n minus r plus 2 and n minus r plus 1, if I expand the bracket, is denoted by NPR, where r represents the number of objects selected and n represents the total number of objects taken into consideration. So n permutation r, which is read as NPR, is given by this formula, is how we understand the formula of NPR. Is very important in taking n dissimilar things. And it's very important to note that by convention we assume that np0 which we have is equal to 1. That is, when r is equal to 0 implies my np0 will always be 1, is how we understand this concept. Because 0 factorial is 1, we will come to a derivation representing this in factorial form, and then we get an understanding that np0 is 1. Now, as we have seen about factorial representation, as we have seen the permutation in the form of the product, now let's see how that can be represented as a factorial notation. Now, redefining the definition of NPR, we know that n is greater than or equal to 1 because n belongs to z plus, and r is always between 0 and n, such that for n greater than or equal to 1 and r lying between 0 and 1 inclusive, I have my NPR, which is denoted by n minus 1, n minus 2 times n minus r plus 2 is what we have taken as the definition. Now let's see how we can represent this in the factorial form. Now revisiting this, we see that this can be written as n times n minus 1, n minus 2, which on further simplification, I get this as n minus r minus 1. For this is r minus 2, and for this can be simplified as n minus r minus 1, is how we get for each of the last two terms in the product. Now, as we see here, I have this to be n times n minus 1, n minus 2, and the last term is n minus r minus 1. Then I try to reduce this by taking as the next term, which is n minus r, and further reducing this, I get n minus r plus 1, and then further n minus r plus 2, and then I multiply with 3, 2, and 1, is how I just try to increase so that I reach to 3 times 2 times 1. So now that I have multiplied, I divide equally with n minus r plus 1, r plus 2, so on and so forth, 3 times 2 times 1. So I'm multiplying this term and dividing equally with the same term to see what exactly we would be getting. So in this case, when I simplify further, I see that this is clearly n times n minus 1, n minus 2 times 3, 2, 1 is nothing but factorial, because n factorial is the successive of each of the consecutive terms as product decreasing by 1 unit. So each of them is decreasing by 1 unit till 3 times 2 times 1. This is clearly n factorial by definition of factorial. And similarly, each of this is also decreasing by 1 unit. We see that n minus r is reducing by 1 unit till it reaches 1. So therefore, n minus r can also be written as factorial, because this is strictly by definition of factorial, as we have seen. Therefore, my NPR is n factorial by n minus r factorial, which we have taken as the formula to be taken through this, where n is greater than or equal to 1 and 0 less than or equal to r less than n, is how we understand the permutation in the factorial form as a formula. Continued in the session. Now let's see what would be NP0 and NPN, which are the special cases of the permutation NPR. So let's take the formula NPR, which we have defined as NPR is n factorial by n minus r factorial, which we have derived in the factorial notation in the previous session. So using this, for n greater than or equal to 1 and 0 less than or equal to r less than or equal to n, let's see how we can derive for each of them. Now, in order that I want to find np0, clearly I take r equal to 0 out there. So r equal to 0 implies my npr reduces to np0, which is n factorial by n minus r, which is 0 factorial because r is 0. So this on simplification gives n factorial by n minus 0, which is n factorial. Because n minus 0 is n, I get overall n factorial down. Now because these two are same, I get this to be 1, which makes me understand that therefore np0 is always 1, is how I understand the formula for np0, which is equal to 1. Similarly, we'll see what is npn. So when I put r equal to n, then I clearly understand that my npn is obtained when r is equal to n. Therefore, this on simplifying with the formula, I get n factorial by n minus n factorial is how I understand this. Now this on further simplification gives me n factorial by n minus n, which is 0. Therefore, 0 factorial by convention is already discussed as 1. Therefore, n factorial by 1, since 0 factorial is equal to 1. Therefore, I get my npn is n factorial and np0 I get it as 1, is how I understand the two special cases. One is np0 and the other is npn, is how we understand the two cases. So now that we have discussed about permutation and its definition in the factorial form, let's see what are the various other properties associated with npr, the permutation of n objects taken r at a time. So we have two important properties. One is npr is always equal n times n minus 1 p r minus 1 is the first property which we identify in case of the permutation npr. Similarly, the second property which is identified is npr is n minus 1 pr plus r times of n minus 1 pr minus 1 is how we understand the two properties where n is greater than or equal to 1 and 0 less than or equal to r less than or equal to n are the two properties which we use in solving of problems to understand the concepts more better in permutations. Properties of permutations are these two. Now let's see some problems where we can use the npr, the number of possible permutations of n dissimilar things taken r at a time. So with an example problem here, I take an interesting example where I want to find the number of 1-1 mappings we know that 1-1 mapping is called an injection in the topic of functions, 1-1 function. Find the number of 1-1 mappings for the following function. Now here there are two sets which form a function, which is set A and then set B. Now here I have a function f which is mapped from set A to set B, such that my question says there are five elements x1, x2, x3, x4 and x5 in the first set A, and in case of set B there are 3 elements y1, y2 and y3. Now we all know that 1-1 mapping is a mapping in which every element has a distinct image. Therefore, I want to know all possible 1-1 mappings which are possible from 5 elements of set A, x1, x2, x3, x4 and x5, and 3 elements of set B which are y1, y2 and y3. So selecting the number of 1-1 mappings out of all the possible mappings is purely a problem based on selection and arrangement. Therefore, we use permutations to find the number of 1-1 mappings which are possible for this function f. So this problem is purely an example problem of a permutation, NPR. So if I see randomly, I see that each of x1 can be mapped to either y1, or it can be mapped either to y2, or it can be mapped to y3. Is how 1-1 mapping is possible for x1 with 3 possible ways. Similarly, x2 with 3 possible ways, x3 with 3 possible ways, x4, x5 also with 3 different possible ways. Now, as I see this with the formula, number of 1-1 mappings for f is nothing but number of 5 dissimilar things taken 3 at a time, is how I understand this. So number of 1-1 mappings for the function f is number of 5 dissimilar things taken 3 at a time. That is, all these come under the NPR, that is, it is possible in 5-3p different ways, is how we understand the number of 1-1 functions. So let's see, when we simplify this, what will be the exact value. So this is given by the formula NPR, that is n factorial by n minus r factorial, which is the formula here being NPR is n factorial by n minus r factorial is what. Now this, on further simplification, gives me 5 factorial by 2 factorial, because 5 minus 3 is 2 factorial. Now here, when I simplify this, I can write this as 5, 4, 3, 2, 1, which is 2 factorial, and then 2 factorial. I can reduce the consecutive terms, reduced by 1 unit each time I multiply the product, so that this 5 factorial can be written as 5 times 4 times 3 times 2 factorial by this, with these two being same, can be cancelled. So therefore, I get this to be 5, 4 times 3, which is 60. Therefore, there are 60 different 1-1 mappings for the function f. That is, we have 60, that implies 5p3 is 60. Therefore, there exist 60 different 1-1 mappings for f from A to B, that is a function f from set A to set B. There exist 60 different possible 1-1 mappings which are distinct for a function f from A to B. That's how I understand, where I need not count of each of the possible distinctions, but can use this formula to understand the permutation connected with number of 1-1 functions. I need not randomly check for each of them, but I can do that using the formula which we have for NPR. So here comes the concept called derangement of things or derangement of elements. So what do we mean by derangement? So let's see the definition before we connect this with permutations. So as we come with permutation, the derangement has its definition, which says that arranging of things in such a way that no thing occupies the original space, such that none of them occupies the original position is called derangement of elements. It is quite opposite to arrangement, because if the destiny is to arrange in that particular place and you're not considering occupying of the original position, then that one which is not considered is called derangement. The process of arranging of things in such a way that none of them occupies the original position is called derangement. So for example, if I have n things, then derangement of n distinct or dissimilar things is given by n factorial times 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial, so on and so forth, till is how we understand this formula. So derangement of n distinct things is given by n factorial times of this is the formula we have for the derangement. So let's connect one example problem where we understand the derangement of things more practical. Now let's see an example problem to understand derangement of elements more clearly. Now as I see here, the problem says find the number of ways in which 4 letters can be put in 4 addressed envelopes. This is a problem related to the postal department, can be put in 4 addressed envelopes so that no letter goes into the envelope meant for it. Now since the statement says so that no letter goes into the envelope meant for it is purely based on derangement of things or derangement of elements, because none of them are occupying the original or the actual position they are meant to be. None of the letter is going into the envelope which actually is meant for that particular letter. So clearly the condition which says that no letter goes into the envelope meant for it clearly is a problem based on derangement of elements, where I have 4 letters and 4 addressed envelopes such that the number of n dissimilar things is n equal to 4. 4 dissimilar things. That implies number of ways is nothing but the formula number of ways of arrangement is nothing but derangement of objects. Therefore, I get this to be derangement of n distinct things, which is given by n factorial, because n is 4. I have n factorial by 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial, as we have seen recently with the formula. Therefore, this on simplification gives, we know that 4 factorial is 4 times 3 times 2 times 1, which is 4 3s 12 2s 24. Therefore, using the factorial definition, I can reduce this to 24 when expanded through factorial. And 1 by 2 factorial is 2, and 1 by 3 factorial is 6, and 1 by 4 factorial is 24. And then taking the LCM of 2, 6, and 24, I can further simplify this to be 24 times of 24, which is 12 minus 6 fours plus 1 is what we get when we expand. Now this on simplification gives 12 minus 4, which is 8, plus 1, which is 9. Therefore, I find that there are derangement of 9 different things. Therefore, the number of ways of arranging is 9 different ways of arranging the 4 letters in 4 addressed envelopes with the condition that no letter goes into the envelope meant for it. Derangement of things using the real life problem. Now let's see the limitations of the permutation. Now that we have discussed permutation as the number of ways in which we can select and arrange, then definitely it has its own restrictions. Say for example, I want to form a 3-digit number using the digits 1, 2, 3, 4, 5. Then I have the independence of using even the digits repeated. But permutation has its limitation, which states that repetition is not allowed. That is, if I have NPR, which says number of permutations of n dissimilar things taken r at a time, then this formula can be used only when n belongs to z plus and 0 less than n, and r belong to z plus and 0 less than or equal to r less than or equal to n is how we have this. And this is true only when assuming repetition is not allowed. Repetition of things is not allowed. So what happens if the repetition is allowed is the biggest question which comes out of the limitations of permutation. Since this is restricted with assuming that repetition of things is not allowed, note here, if repetition of things is allowed, then number of ways in which n dissimilar things be arranged taken r at a time is given by n power r, that is n times of r times. So this is when repetition is allowed, and this is when repetition is not allowed, is how we understand. So when repetition is not allowed, NPR is n factorial by n minus r factorial. When repetition is allowed, I have NPR is n power r, is how I understand the difference between repetition is not allowed and repetition is allowed. Now, the formula here says if I want to find the permutation or the number of possible permutations of n dissimilar things taken r at a time with at least one repetition allowed, we'll see how we can derive a formula for such a situation. So, number of possible permutations of n dissimilar things taken r at a time with at least one repetition allowed will be all the number of possible permutations where repetition is not allowed minus all the number of possible permutations where repetition is allowed minus not allowed. So therefore this clearly gives me with the formula n power r minus npr, because this is when repetition is allowed and this is when repetition is not allowed. So removing all the possible permutations where repetition is not allowed, we get at least one possible repetition allowed. We get at least one permutation with a repetition allowed. So here, in this case, repetition allowed, and in this case, not allowed. Therefore, I get this to be n power r minus npr is what we derive as the formula for this case, where I want to find the number of possible permutations where at least there is one repetition which we take into consideration. So next is palindrome, which is an English word, or the definition is more in the grammatical context of the language English. But this plays a vital role in the topic of permutations and combinations, because arranging or selecting through and arranging through selection is totally based on this important concept. So let's see what is palindrome. A number or a word which reads the same from left to right and from left to right and from right to left is called a palindrome, is how we define a palindrome. We have many examples in the words which we see in the sentences of English context of dictionary, where I have this as this thing. Madam, all these, and even which you see in the advertisement, are all palindromes. And when I take numbers, these are all examples of palindromes which you see in daily life. So coming to these, we call them as palindromes because when you read from right to left and left to read right, they are same. Interestingly, there are some sentences which are also palindromes. Interestingly, there are some sentences which are also palindromes, like rats live on no evil star. When you just reverse it, you get the same sentence read as read from to back. Even when I take the letters of the word jumbled, in this case, so this on reversing gives us the same letters when read from last to the first. So these are all examples where, was it a car or a cat, I saw rats live on no evil star and rats live on no evil star when read from last to the first. So these kind of examples make us understand that palindromes are the numbers of words which read the same from left to right and from right to left, as with examples out here. Now that we have discussed about palindromes, let's see how we can derive the formulae for connecting the palindromes with permutations. Say for example, I have totally n things out there, out of which r things. So out of n things, r things are selected and arranged as palindromes. So out of n things, r things are selected and arranged as palindromes. Then the number of palindromes which can be formed, or where r things are taken out of n things, is given exclusively by the formula which says number of palindromes formed from n words or numbers taken r at a time is given by the formula which says it is n power r by 2, n power r by 2 if r is even, and this is n power r plus 1 by 2 if r is odd, is how we understand the formula which connects the number of palindromes formed from n words or numbers taken r at a time. So this is the formula which we use in finding the number. Where r is even, we use this formula. If r is odd, we use this formula. This is how we understand the palindromes connected with permutations. Now here the question says find the number of 7-digited palindromes that can be formed using the letters 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the question is purely based on finding the number of palindromes that can be constructed from taking 10 objects and selecting 7-digited numbers out of that. So this can purely be connected to the permutations in the following manner. Now clearly I see that the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are totally 10 numbers as given in the given problem. Now from here I pick 7 of the numbers to form 7-digited numbers, but the rule is that they need to form palindromes. So as we have seen the formulae connected with palindromes for r even and r odd, clearly to form 7-digited numbers, I see that from the given problem r is 7, which is even, which is odd. Now since 7 is odd, this comes under the case of r odd. Therefore, number of palindromes which can be formed out of these 10 numbers picking up the 7 digits to form the 7-digit palindromes is nothing but n power r plus 1 by 2 when r is odd is what is the case I consider here, because simply r is equal to 7, which is odd. Now substituting n and r, I get this to be 10 power 7 plus 1 over 2, which comes as 10 power 8 by 2, which is 10 power 4. So this on cancellation gives me 10 power 4, which is 10,000. That is the totally 10,000 different palindromes which can be constructed as 7-digit palindromes. Therefore, the number of 7-digit palindromes which can be formed using the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 is 10,000. The number of totally, there are 10,000 different palindromes of 7-digit numbers which can be formed using the numbers 0, 1, 2, 3 till n, is how we understand the number of palindromes as connected through the permutations. Now let's see the other type of permutation called circular permutation in brief. So as in the previous session we have already discussed that there are two types of permutations. One is linear permutation and the other is the circular permutation. Now to discuss in brief about circular permutations, let's recap with the definition which we have already discussed for circular permutation. which says arrangement in a circle. The word circular implies that the arrangement which is considered is in a circle, in a circular form. Is how we understand the circular permutation. For example, the beads in the necklace, or we have so many other examples like I want the conference of the people sitting around the round table conference. So these are some of the cases or the situations where we need to use the circular permutations. But we have to identify that there are two types of permutations which we need to take into consideration, because if we take this in the form of a circle, then I identify that my circular arrangement of, say, 1, 2, 3, 4 and 5. If I wanted to arrange 5 members in the circular form, I can either arrange from here to here, or this person can sit here and this person can sit here in such a way that I have the persons sitting in the form 1, 2, 3, 4 and 5. So the difference between these two types of arrangements is that here we have things in clockwise direction and here we have things in anti-clockwise direction. So arrangement of the 5 persons 1, 2, 3, 4 and 5 here is in clockwise, and this is in anti-clockwise arrangement. So here we call this as clockwise arrangement. And it is also possible that I can arrange the 5 persons across the round table in an anti-clockwise arrangement. So this is how the clockwise and anti-clockwise arrangements are done in case of circular permutations. Now, here comes the question on what is the need for taking this and this. This we will come across when we do many problems and identify whether we really require a case where we can arrange the persons or the beads or whatever is the situation in a clockwise or an anti-clockwise direction. Because when I have, say, I put the beads in the necklace, it doesn't matter whether I put from clockwise or anti-clockwise. But if I arrange the persons in a round table conference, it may be that we need to take into consideration the clockwise or anti-clockwise direction into existence, the possibility of this. So let's see when we use the clockwise arrangement and when we use the anti-clockwise, or we give a freedom of using either this or this at a given problem, is how we understand with the future problems in the continued session. So here I make a note that because I have two types of arrangements which I need to take, clockwise and anti-clockwise, my learning outcome in circular permutation is that circular permutation takes direction into account. That is, it is important that even direction is taken into account, is how we understand the circular permutation more better. So circular permutation takes direction into account. Let's see some problems to support this. So let's see the formula for calculating the number of circular permutations which is possible. Or for example, let's take the previous case of 5 persons sitting across a round table. Let's see how many different possible circular arrangements I can make in changing all the 5 persons in different orders in across this round table. So with these problems, we have a specific formula which we are going to discuss in the session for finding the number of circular permutations possible for n. So here, let there be n things out there which are taken into consideration. So for these n things, number of circular permutations for n dissimilar things, because I don't take them as common but each of them is distinct, for n dissimilar things taken all at a time, because this is important, because I don't neglect even one of the thing out of n things. Taken all at a time is given by the formula n minus 1 factorial. So this is the formula for finding the number of circular permutations for n dissimilar things taken all at a time, is given by n minus 1 factorial, is how we understand this through this. Now you have a specific note here where if I don't take the direction, or if I don't take the clockwise or anti-clockwise direction into account, let's see how we have an extended formula. Now for cases where I want to find the number of circular permutations where putting the beads in a necklace or putting the flowers in the garland, then in these cases it doesn't matter whether I put the flowers in the garland from clockwise direction or anti-clockwise direction. It ultimately makes a garland. So in that case, the direction is not taken into account. So in case of these kind of problems of beads or garlands, let's see how this formula is restricted. For circular permutations, which does not take direction into account. So in this case, if it does not take direction into account, for example, beads of necklace or flowers of garland, etc., then in that case I have the formula which reduces in this form. Then in that case, number of circular permutations of n dissimilar things taken all at a time is given by n minus 1 factorial by 2, because it is the anti-clockwise or clockwise direction which are one and the same. Therefore, by getting n minus 1 factorial for the formula for the number of circular permutations where direction is not taken, where the direction is taken into account, that is both clockwise and anti-clockwise are taken into account, exactly half of this cut shorts on the direction of either clockwise or anti-clockwise. So half of this would be the number of circular permutations of n dissimilar things taken r at a time. But in this case, direction isn't taken into account. Is very important in understanding the problems which have direction to be considered and the problems which doesn't have the direction to be considered. If the direction is considered, then I have the formula n minus 1 whole factorial for finding the number of circular permutations. And if the direction is not taken into account, for example cases of beads of necklace or flowers in a garland, etc., then my number of circular permutations is exactly half of n minus 1 whole factorial. Is how I understand the concept. Now let's see an example problem to understand the circular permutations more better. So here the question says find the number of ways of arranging five boys and 3 girls around a circle. Now here I clearly identify the circle and hence the arrangement or the permutation is a circular permutation. In this case I want to find the number of ways of arranging 5 boys and 3 girls around a circle. Then definitely I take direction into account because it really matters if I make them arranged in a clockwise or anti-clockwise direction. So therefore there are 5 boys and 3 girls which give us direction is taken into account in case of the circular permutation. Therefore, and here my n is totally 5 boys and 3 girls, that is 5 boys plus 3 girls, which comes out to be 8. There are totally 8 persons or 8 students out there. So using this n, I want to find the number of circular permutations of 8 dissimilar things, because n is 8, of 8 dissimilar things taken all at a time is given by n minus 1 factorial as the formula, and then we know that with this formula I can substitute n is equal to 8, which gives me this equals 7 factorial, and 7 factorial is found by substituting this as 7 times 6, 5, 4, 3, 2 and 1. Now this comes to be a very lengthy process where I get 7 times 6 5 is 30, 30, 4 3s are 12, 12 2 is 24, 727. So this comes out to be 5040. So there are 5040 different ways of arranging 5 boys and 3 girls around a circular form, where half of them would be in the clockwise and half of them are in the anti-clockwise direction. So exactly, it is an interesting note which make that if I have 5040 by 2, which comes out to be 2 2s 4, 2 5s 2 0, which shows that 2540 ways to be arranged, ways of arrangement in clockwise direction and the rest in anti-clockwise direction, and the rest in anti-clockwise direction. So this makes us understand that when we get the answer in case of direction which is taken into account, half of them would be in the clockwise direction and half of them in the anti-clockwise direction. Now let's see a problem where direction is not taken into account. So if I have a problem, say find the number of chains that can be prepared using 7 different colored beads. is the question out here. Now this is a problem which is based on using the beads, the 7 different colored beads, and forming a chain. If suppose I just want to use say I want to make an arrangement of 7 different colored beads, which I'm using here to make now in this case of the necklace. Let's see how it is possible that I can make an arrangement. Now it doesn't matter whether I go in the clockwise or anti-clockwise direction in case of using 7 different colored beads. So here the direction makes us with direction is not taken into account, because it doesn't matter with the direction which I'm going to take into account. Therefore, the number of circular permutations is exactly n minus 1 factorial by 2 is what we take if the direction is not taken into account. And clearly we know that n is equal to 7 because there are 7 beats. So using this, I get 7 minus 1 factorial by 2, that is 6 factorial by 2, which is nothing but 6, 5, 4, 3, 2, 1 over 2, and then 6, 5 is 30, 30 times 2, 360 different ways of arranging the beads, the 7 colored beads. There are 360 different ways through which you can arrange the 7 different colored beads, and the number of chains that can be formed is nothing but the number of ways you can arrange. So there are totally 360 different types of chains you can make with 7 different colored beads, is how we understand the problem. So therefore the problem here says that therefore (360) different chains can be prepared using seven different colored beads, is how we understand this situational problem. Now let's see the permutations with constraint repetitions. Now this is a limitation of a permutation, because in general, if we had all different letters, say for example, if I had the letter word, then the number then the different possible permutations which were possible through this, the number of arrangements I can make was n factorial, that is 4 factorial, which is nothing but 4 3 is 12 is 24. That is, there are 24 different ways of arranging all the 4 letters of the word read, R-E-A-D. Now what happens if I use the word assassination? Now clearly the difference between this word and this word has a wide difference, because if you identify, I have some repeated letters, like there are 4 S's and 3 A's, and you have 2 I's and N's are 2 and 1 T and 1 Whoa. Now in this case, this S repeating 4 times and A repeating 3 times and I repeating twice and N repeating twice, of course, and whoa are not repeating, makes us understand that there is a wide difference between the word read and assassination. In this case, there are no repeated words, each of them are dissimilar. So if you have n dissimilar things, we can use the formula NPR, but if you don't have n dissimilar things, that is, if you have a combination of like and unlike, so all these are likes, and this is unlike. So in this case, there are some similar things out there. So combination of similar and dissimilar things makes us understand that this permutation or the number of permutations I can make with this cannot be used with the formula NPR. Definitely, this will not be applied. Or if there's a continuous repetition, I can use the formula n power r, but in this case, when you have a combination of similar and dissimilar things, then we get with constraint repetitions. So let's see how we can find the number of permutations where the repetitions and some of them repeat and some of them do not repeat. That is, if you have repetitions included, like and unlike things, then let's see how the formula is derived for this kind of a situation. Now let's see the formula where if I wanted to find the number of permutations of n things, but I don't take n dissimilar things here because some of them are alike and some of them are not. So number of permutations of n things in which p are alike, that is, there are p of them which are alike and the rest are different, is given by the formula n factorial by p factorial. That is, all the like factorial are taken in the denominator. Therefore, this reduces to the formula number of circular permutations of n things in which p are alike and the rest are different is given by this. Now the same problem formula, if I extend with n things, if there are n things in which p are alike q are alike and r are alike, then in this case, if I have p, q and r which are all alike in their own way, then I have number of permutations in this case is given by n factorial by p, q and r. So it goes on and off in that way through which I can use the formulae as according to the given conditions. So if you have p and q alike terms, then I can use n factorial by p factorial into q factorial. So the formulae change accordingly with the alike terms and the non-alike terms. Ultimately, the basic formula being the number of permutations of n things in which p are alike and the rest are different is given by n factorial by p factorial. So if there are 3 of them which are alike, then all the 3 come independently in the denominator as the product. If 2 are alike, then I get this as n factorial by p factorial into q factorial, is how we understand this. Now let's do some problems to understand this concept more better. Now let's see an example problem to understand the permutation with constraint repetitions. So if I take a problem which says find the number of ways of arranging the letters, arranging the letters of the word mathematics. So let's see how we can do this with the constraint repetitions. So initially, let's take the word which is given out in the problem, which is mathematics. Now in this case, clearly we first identify n, that is the number of letters in the given word. Now clearly the number of letters in the given word are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So totally there are 11 letters in the word mathematics. Now let's see how many of them are repetitive or alike. Now as I clearly see here, there are 2 M's which are alike, and similarly I see that there are 2 A's which are alike, and there are 2 T's which are alike, and there is nothing else which is alike. Mathematics. 2 T's, 2 M's and 2 A's which are alike. Now in this case, these are all the like terms where this is P, this is Q, and this is R, which we have already discussed as the formula in the previous session. Therefore, number of ways of arranging the letters of the word mathematics is given by the formula n factorial by P, Q, and R is how we get the formula. Now here n is clearly 11, so I get this as 11 factorial by P factorial, which is 2, Q factorial, which is 2, and R factorial, which is also 2. Now the question comes on simplifying this. So let's see how we can simplify this, because 11 factorial is 11 times 10, 9, 8, 7, 6, 5, 4, 3, 2 factorial. And you have 2 factorial which gets cancelled, and 2 factorial is nothing but 2, because 2 factorial is 2 times 1, which is 2. Therefore, I can substitute for 2, and this gets cancelled with this. Then finally, I am left with 11 times of 10 times 6 5 is 30, 33 is 90, and then I multiply and simplify all these so that I get 9 8s are 72, 11 times of 900, and 9 8s 72 times 7, which gives me 7 9s 6300 times 72, and then 63 times 72 is 3 2s are 6, 6 2s 12, 7 3s 21, 6 7s are 42, 44, 6, 3, 5, 4. So I get this to be 4989600 is how I get. There are this many ways of arranging the letters of the word mathematics. So I can arrange the letters of the word mathematics in jumbled form in 49,89,600 ways. So it is 4989600 times number of ways through which I can form the letters arranged in different forms using the word mathematics. So the answer is according to the permutations with constraint repetitions. Now that we have discussed about permutations, the next concept which comes is combinations. As in the previous sessions, we have already differentiated between the understanding of permutations and combinations. Let's recap with the similar session. Now, as we have discussed with permutation as the selection and then arranging them in order, then combination is only selecting but arranging or taking into account the arranging in order is not taken into account. That is, a combination is only a selection. A combination is only a selection. Suppose I want to select a team of 11 players from the class of 40 students, then that is purely based on a problem related to combination. That is, if I take a situational problem where I select a cricket team of 11 players from a school consisting of 300 students, is purely a problem based on combination. Combination situation. So we need to identify through the given problem whether a problem is based on permutation or a combination. Now this problem is clearly selecting a cricket team of 11 players from a school consisting of 300 students is clearly a problem based on combination. But if I wanted to arrange those players in a proper order, then the question comes on arrangement, and hence we try to consider arrangement in case of permutation. So permutation is selecting and arranging, a combination is only selecting. So we know that a cricket team of 11 players doesn't require any arrangement and order. Therefore, I have a cricket team which says the selection being combination. So we have different ways of understanding the combinations through the selection. We will see how we can derive a formula for a given problem which is related to combination. So continued with the session. Now here, let's derive a formula for a combination. So in this case, I define the number of possible combinations, the number of possible combinations of n dissimilar things taken R at a time is denoted generally with NCR, or it is denoted with NCR, or it is also denoted with NR, and this is given with the formula, or this is also denoted. There are so many different ways of denoting this, or NCR, C and R are the various notations, and it is given by the formula n factorial by n minus r factorial into r factorial is how we derive the formula for number of possible combinations of the n dissimilar things taken R, is how we get this formula. Say for example, in how many ways can 3 people be selected from a group of 6? So in this case, let's see how we can just use the formula for finding, because it is only about selection but not arrangement. So this is purely a problem based on combinational situation. So here I clearly see that the total number of people in the group is n, which is 6, and the number of people I'm selecting, which is 3, is R, taken 3 at a time. So using n equal to 6 and this, the number of possible combinations is, so that implies the number of ways of selecting will be 6C3 as I see NCR, but given by the formula 6 factorial by 6 minus 3 factorial into 3 factorial, which can be simplified as 6 into 5 into 4 into 3 factorial, because it ends with this using the factorial formula. And 6 minus 3 is 3 factorial, and 3 factorial is 3 times 2 times 1, so that I cancel this. 3 2s are 6 and 6, I get 5 4s 20. That means there are 20 ways through which I can select 3 people from a group of 6 people, so which is possible in 20 different ways of selecting, is how I understand the problem based on combinations using the formula NCR equals n factorial by n minus r factorial into r factorial. NCR with its various notations, which can be denoted by this or this or this or this. There are 4 different ways of denoting the combination NCR. C stands for combination. Is how I understand the combination. Now here, now that we have defined the definition, or we have derived the formula for NCR and NPR, let's see how NPR and NCR are related through their respective formulae. So we have NPR, which is defined as n factorial by n minus r factorial, and my NCR, which is derived to be n factorial by n minus r factorial times r factorial. So these two formula clearly makes me understand that there is NPR in NCR. So as I clearly see that this is nothing but the NPR which I see over on the left side. So we definitely have a relation between NCR and NPR when this whole of this is substituted in NCR. So therefore, that implies NCR, which is n factorial by n minus r factorial into 1 by r factorial, which can be arranged, makes me understand that this can be substituted with this, so that n factorial by n minus r factorial is NPR by r factorial. That implies my NPR is defined as r factorial times NCR, is how I see the relation between NPR and NCR. Therefore, NPR is r factorial times of NCR, or NCR is NPR by r factorial, is how we see the relation between NCR and NPR, where P stands for permutation and C stands for combination, is how they are related. The permutation and combination are related with the formula NPR is r factorial times NCR. So let's see the special cases of finding NC0 or NCN. So we'll see these two as the special cases for NCR, because r is fixed at 0 and r is fixed at n out here. So let's see how we can derive the values for NC0 and NCN. Now we have NCR is n factorial by n minus r factorial into r factorial, where n is greater than or equal to 1 and n belongs to z plus, and r always lies between 0 and n, is how we understand the concept. Now in this case, when I want to find NC0, I fix r equal to 0, then that implies I get NC0, and let's see what this reduces to when I substitute r equal to 0 here. So I get this with r equal to 0, n factorial by n minus 1 0 factorial times 0 factorial, which on further simplification gives n factorial. N minus 0 is n factorial times 0 factorial. Now this gets cancelled because n is not equal to 0. Since n is not equal to 0, I can cancel, and this reduces to 1 by 0 factorial. And we all know that by convention 0 factorial is 1. Since this is 1, I reduce this to 1. Now this implies I get 1 by 1, which is 1. Therefore, I derive that NC naught is always equal to 1. That's how I understand the first case of NC naught, which is 1 for all n belonging to Z plus. Is how I understand this. Now let's see what would be the value of NCN, where I'm going to substitute R equal to n in the case 2 of this. Now when I substitute R equal to n, then my NCR, which is this, gets reduced to NCN, which is n factorial by n minus n factorial times n factorial, because R is n, it gets replaced with R equal to n on the right side of the formula. So this would be n factorial, n minus n, which is 0, times this. Now this can be cancelled since n is not equal to 0, where n is a positive integer, so n is not equal to 0, therefore this can be cancelled, so that this reduces to 1 by 0 factorial, which is 1 by 1, because we know that 0 factorial is 1, and therefore NCN is equal to 1 for all n belonging to Z plus. So we have two important formulae. One is NC naught equal to 1 and NCN also equal to 1, which we observe. Also, the interesting thing which we note here is that NC naught is always equal to NCN for all n belonging to Z plus, is how we identify, and this is of course equal to 1 as we have derived here. But basically my NC naught is 1 and my NCN is 1 for all n belonging to the set of positive integers. Is how I understand the special cases of NC naught and NCN. Now let's see some properties of the combinations NCR. Now the first combination out here is the property NCR is equal to NC n minus R, is one of the basic property which we identify for n belonging to Z plus and R belonging to Z, such that 0 less than or equal to R less than n, then I have NCR is always equal to NCn minus R. That is, for example, if I wanted to find C of 98, that is n is 100 and R is 98, then this with n equal to 100 and R equal to 98 implies this can be converted using NCn minus R, which is nothing but n, which is 100 C, 100 minus 98, so this is 100 C2 is what we get. Therefore, the 100 C98 which I wanted to find would be equal to nothing but 100 C2, is how we understand this formula. Now the significance of this formula is that if you have the larger R can be reduced to the smaller r using the formula. So significance is that it helps in reducing the value of r, making the simplification more easier. Helps in reducing the larger values of r. As can be seen here, this reduces to 2 from 98. This reduces all the way to 2. So making the simplification more easier helps in reducing the larger values of r is the most important part of this formula. Now, combination also helps us in dividing into groups and finding the number of ways in which we can form the groups, the different groups. To be more clear, let me take an example of, say, I have a group which has m plus n things out here. There are m plus n people or things inside the group. So this group has m plus n things, and now I want to divide this into two groups, where I want to divide them into a group of m things and then a group of n things. Then I want to find the number of ways in which I can do where I can divide m plus n things into group of m things and n things. So the different possible ways of dividing these into these m and n things is what is combination, and it has an exclusive formula, and we will see how we can find the number of ways of dividing m plus n things into two groups of n things and n things respectively is equal to m plus n factorial by m factorial into n factorial is the formula. And of course we know that m and n are positive integers which we identify here, may be distinct or may not be distinct. Now here the different possible ways of dividing m plus n things into two groups of m things and n things respectively is m plus n factorial by m factorial into n factorial is how we understand the formula. And note here m plus n cm is nothing but m plus n factorial by m factorial into n factorial. Therefore, this is how we get this connected with this. So let's see one problem supporting the previous formula related to dividing into groups. So the question here says, find the number of ways in which a group of 10 students be divided into two groups with group A containing 6 students and group B containing 4 students. Now here this is purely based on dividing into groups because a class consisting of 10 students is divided into a group of group A, which consists of 6 students, and group B, which consists of 4 students, is how I need to divide the group of 10 into 6 and 4. Now here clearly I identify that for this particular problem, my group A with number of things being 6 and n being 4 is going to use the number of ways, number of possible ways which uses the formula n plus n factorial by n factorial times n factorial, which we have already derived, and thus using the formula I have 6 plus 4 factorial by 6 times 4 factorial, and then simplifying this continued, I get this to be 10 factorial by 6 to 4 factorial, then 10 factorial, which I can write 10, 9, 8, 7, 6 factorial by 6 factorial times 4, 3, 2, and 1. This gets cancelled and I get this 4 1s, 4 2s, 2 gets cancelled, 3 1s, 3 3s, and then I get 7 3s, 21 times 10, which is 210. Therefore, there are 200 different possible ways through which I can divide the group of 10 students into a group containing 6 and a group containing 4. So 200 different possible ways of division into groups is possible through the formula m plus n factorial by m factorial into n factorial. Now, if suppose I have equal groups which I need to divide into. In the previous case, the two groups were with not equal number of students as taken in the previous problem. Now, suppose I want to divide the same 10 students into equal group of 5 students and 5 students, that is 2 equal groups. Then in that case, we have a slightly modified formula for the previous session. So in this case, if I have, say, 2n dissimilar things which are not equal but they are distinct. For this 2n dissimilar things, if I want to divide into 2 equal groups of n things, half of this, then exactly this will be half, the other half, which is again n things. Now therefore, this in case of such a situation where I want to divide the group, original group, into 2 equal subgroups, then this is possible with number of possible ways is given by the formula of dividing the given group into 2 equal groups is given by the formula 2n factorial by 2 factorial into n factorial, and this is how we get the formula. Or this can also be written as 2n factorial by 2 factorial n factorial whole square is how we get the formula. This is how we understand the formula with equal groups out there. Now suppose I have a case where in the original group there are mn things. Say I assume that in the original group there are totally m times n things, and I want to divide this group containing n things and thus again into a group containing n things, that is m equal groups which I am taking here, because each of the group is having n things. When you add up till m times, I get mn. So mn things in the original group can be divided into m groups containing each with n things. So in case of this, how do we do the number of possible ways of using the formula? This kind of a problem can be done using the combination, which is nothing but number of possible ways is given by the formula is given as mn factorial by m factorial n factorial whole power m is how we understand the formula related with this. So like this, different problems with m groups with each one having n things can also be found using the respective formula. Now next is a slightly modified formula where the number of ways of distributing or dividing mn things equally among, say, m persons. I refer to persons because I want this to be understood in the form of distribution, which makes this topic be understood more better in this particular session. The number of ways of distributing mn things equally among m persons is done through mn factorial by n factorial whole power m is how we understand the formula through its respective definition. So like this, we have different groups, different properties which we identify in combinations through the respective formulae in the topic division into groups in various forms. So the previous topic which we have discussed is related to the word at least, because when we do this example problem, we understand on how one or more is referred as at least. Say for example, the question is find the number of ways of selecting at least 3 books from a shelf of 5 books is the question here. Now this is purely related to the word at least, which says 1 or 3 or more than 3, because at least 3 implies 3 or more than 3 is how I understand the word at least 3. So in this case, I clearly see that the total number of books in the shelf is 5, which refers to n equal to 5. Therefore, using the formula, number of ways of selecting at least 3 books out of 5 books is possible using the formula 2 power n minus 1, which gives me 2 power 5 minus 1, which is 32 minus 1, which gives me the answer as 31. That is, there are 31 possible ways of selecting at least 3 books out of the 5 books in the shelf. Is how I understand at least as 3 or more than 3, at least 3. So let's discuss about the positive divisors, that is the divisors which are greater than 0. So what are divisors? How do we understand the concept of divisors? Say for example, I have the number 12. What are the divisors for 12? If suppose I find all possible numbers which divide 12, I observe that 1 divides 12 and 2 also divides 12, that is 2, 6, 12, that is 12 divided by 2 is exactly an integer. Then I also see that 3 4s are 12, so 3 is also a divisor, and then 4 is also a divisor. 5 is not a divisor because I cannot write 5 as multiple of 12. 5 times no integer gives me 12. Then again 6 is a divisor because 6 times of 2, 6 2s are 12. Then finally I have 12. So I find that 12 has 1, 2, 3, 4, 5, 6 divisors. That means the numbers which divide 12 are called the divisors. So in case of 12, there are 6 divisors is how I understand, of course, which are positive is how I understand for the number 12. So every number has a specific number of divisors, positive divisors, which we can find using the combinations. The combinations helps us in identifying the number of positive divisors of a given positive integer. So let's see how we can derive the formula for finding the number of positive divisors of each number. For 12 being 1, 2, 3, 4, 6, 12, 6 divisors which are positive. So the number is big. If you can imagine that finding the positive divisors through this direct process may not be easy. We need to search for a shortcut formula for a very high or a large number. So let's see how we can derive the formula for finding the number of positive divisors of a positive integer n, however large or however small the integer is. Now let's consider a positive integer. Let m belong to z plus such that I can write m as p1 alpha power alpha 1, p2 power alpha 2, p3 power alpha 3, so on and so forth till pk power alpha k, where each of p1, p2 till pk are called distinct primes. That is, if I can express a number as the product of primes, then each of the base is a distinct prime and the indices are obviously integers which we see. Then in this case we have alpha 1, alpha 2 till alpha k, which are called positive integers. Then under this condition, the number of positive divisors of m, the positive integer m expressed as this form, is given by the formula directly: alpha 1 plus 1, alpha 2 plus 1 till alpha k plus 1 is how I understand the formula for finding the number of positive divisors of m. Is how we get the number of positive divisors. And note that the trivial divisors 1 and the number itself are included in this. It is a very important note that 1 and m itself are also included in this product. That is, in the number of divisors, 1 and m itself are also included in this, and these two are called trivial or improper divisors of the given number. So if I wanted to find the number of non-trivial or proper divisors, then that will be too short of this. Therefore, if I extension of the formula, I have number of positive divisors, positive, non-trivial or proper divisors of m is nothing but excluding 1 and m, which are 2 in number. Therefore, I have the same formula where I subtract 2. Is what is very important. So when I want to find the non-trivial or proper divisors, I have the formula which has -2. When I wanted to find the positive divisors, which includes both trivial and non-trivial or proper or improper divisors, then I have the formula which is this. The trivial or improper divisors defined as 1 and itself is how we define the trivial and improper divisors. So let's see one example problem to understand this concept more better, to be continued in the session. Now let's take an example problem and find the number of positive divisors as we can see in each of the cases. Let me take the number 300 for which I want to find the positive divisors. Now, as I randomly see, I can at the most find the divisors of this as 1, 2, 3, 5, 6. Then once I go, it is very difficult as I approach with higher numbers, because reaching up to 300 to find the positive divisors or the numbers which divide this may not be an easy task for such large numbers. But if I have a number 12 or 24, I can easily find the divisors for this, because I can see 1, 2, 3, 4, 6, 8, 9, 10, 11, 12 and 24 is how I can find the number of divisors as 1, 2, 3, 4, 5, 6, 7, 8. There are 8 positive divisors for 24. Because this number is smaller, I can easily find through the random approach. But this number being very large, it is not an easy task. Not an easy task to find all the positive divisors. Therefore, we use the formula which we have derived using the combinations, and then we can find the number of positive divisors for this number 300. So before we try to find the number of positive divisors, I take the number 300 and write all possible factors, or expressing this as a prime factor. That is, if I take 300 and find its factors, I have 3 hundreds, 5 20s, 5 4s, 2 2s, 2 1s is how I get this. That is, this can be written starting from the least prime as 2 square times 3 times 5 square is how I understand this in the form of prime factors, expressing this as a prime factors. Now, as I see clearly here, when I compare this with the formula, my P1 is 2, my P2 is 3, and my P3 is 5, each of P1, P2, P3 being the basis, and the powers of the primes are alpha 1, alpha 2 and alpha 3, which are alpha 1, alpha 2 and my alpha 3, which are given by this. Now, to find the number of divisors which are both trivial and non-trivial, or proper and improper, then therefore number of positive divisors of 300 are given with the formula alpha 1 plus 1 times alpha 2 plus 1 times alpha 3 plus 1, which stops at alpha 3 because k is 3, and here this is m equals 300. And therefore, using the formula for m, number of positive divisors of 300 is directly given with the formula this, which on substitution of each of alpha 1 gives me 2 plus 1 in place of alpha 1, and 1 plus 1, and next is 2 plus 1, which gives me 3 times 2 times 3, which is 18. Therefore, we understand that there are 18 positive divisors in the number 300. Therefore, 300 has 18 positive divisors, out of which 18 minus 2, which is 16, are non-trivial divisors, and 2 are trivial or improper positive divisors. In this case, 1 and 300 being the divisors is how we understand for any large number we can just conquer the divisors using this concept. It is not an easy task using the formula in finding the positive divisors of very large numbers, especially using the formula.